the other people that am I not allowed, or it is just
no, just
okay,
turned cameras off.
okay, very well. So I'm trying to share my screen now. Let me see if that would be possible, and let me see if you see that. Can you see that?
Yes,
Okay,
everything's
if
okay.
I go to the presentation mode, can you see that also?
Yes.
Okay, so I think I can start if you like.
Yes, please.
Okay, so good afternoon, everybody. As Anatoly said before, I'm Professor Paolo Porto from the University Mediterraneo of Reggio Calabria. Reggio Calabria is a town in southern Italy. I don't know if you can see my pointer here. Can you see it? My pointer?
Yes.
Okay, so the city is located right here at the end of the peninsula. You can see that, and yeah, my university is right there, and I work there as a professor teaching soil erosion and soil conservation strategies, and also torrent control and catchment management. Today, I'm going to talk about soil erosion, and more specifically, I'm going to talk about the technique which is based on the use of cesium-137, which is a radio tracer. And I'm going to talk about two kinds of approaches that make use of this radio tracer. The first one is called a traditional approach. I will give you later details about that. And the second one is called the resampling approach, which is a more sophisticated approach using the same radio tracer. You can see here in this picture the field area where this technique was applied. You can see here, I don't know if you are familiar with soil erosion measurements, but these are 5 experimental plots, same size of those used by Wishmaver and Smith in their long-term studies on soil erosion. So they have 25 meters of length and 5 meters of width, and they have a slope of 9–10%. Okay, so what I'm going to talk about, the application of this technique, is related to the field area that is located and is represented by this picture. So before going to the specific point, I just want to give you an overview of the methods for estimating soil erosion. I'm assuming that you are familiar with soil erosion and you know what soil erosion is and what it causes. But here I want to tell you how soil erosion can be monitored, measured, and or estimated. So in general, as a general point of view, we have 3 types of methods. The first one, well, I called it measurement techniques because it is based on direct observations of soil loss. And these techniques, as I said before, make use of experimental sites like plots, like the ones that I showed you before, or catchments. And going back to the field area that is monitored by my university, you can see that similar areas are equipped with sediment collectors. These tanks, one for each one or more than one, depends on the size of the plots, that are located at the base of each plot. And these are in charge for collecting runoff and sediment. And also for each experimental plot, we need a meteo station, which gives us, the more important climatic variables like rainfall and temperatures, radiation, and so on. So in the end, in similar sites, we have we know how much rainfall comes to the ground, how much rainfall is collected by the tanks as a runoff, and how much sediment is removed after each event. Okay. So what about the advantages of this first technique? Well, first of all, they are very precise because it's a closed system. So we know exactly how much it rains, how much it is washed away by runoff, and how much soil is removed from that area. But the problem is that they have also some inconvenience that are related to the fact that they are small in size. And so when you have to extend the results obtained in this kind of experimental sites, it is difficult because you need the same characteristics on larger areas. And this is difficult to be obtained because when we talk, for example, about a large catchment, it is difficult that all the variables are uniformly distributed like within the small plots. And so we need to account for the boundary effects. We need to consider that these measurements are at-site measurements that cannot be extended if only in particular cases. But most importantly, they are very expensive, and because they are time-consuming, and because in order to have a representative value of soil loss, you need at least 15-20 years of measurements. That means a lot of work, because you have to consider that we have to collect the sediment in the tanks for each event. So depending on the number of events that you have each year, let's say 15, 20, 30 events, well, depending on the climate, you have to go to the field 15, 20, 30 times to collect the turbidity, and to go to the lab to dry the samples, and then to have one data for each event. So if you have, as I say, the 20, 30 events per year, you have to do these 20, 30 times to get the value of that year. So in order to have a representative value of soil loss that is measured in tons per hectare per year, you need to multiply this activity times 15, 20 times. That's the number of the years that you need. And so this means that it is very expensive in terms of number of people involved and time that you have to devote to this kind of operations. Also, another important inconvenience about this approach is that it is not retrospective. What does it mean? That if I want to study soil erosion and I just equip these sites, I can study soil erosion, I can monitor soil erosion from now on, for the next 20, 30, 40 years. depending on the duration of my life and my cooperators. But I don't have information of the past. Okay, so for this reason, some other people try to make use of the second method for estimating soil erosion, which makes use of mathematical models. Now, there are so many models in the literature. I just mentioned some of them. USLE, for example, is the most common, most known method for soil loss calculation. And we have also many other USLE derived or refined model like Russell, Muzzle, and so on. And you can see also other names like WEP or SWOT. This one, the last one, for example, the SWOT is very well known today, very much used. But, there are many others. But one of the main problems related to the use of these models is that they need calibration and validation, because we cannot use models without doing calibration, because most of them were built in areas that are not the same of the areas of application. And then in order to apply them, you need at first to select a certain number of years for doing the calibration, see how the parameters react to this calibration exercise, and then you have to select some other years of measurements in order to validate the model. And that means that you need the measurements. So you need the first method at the same time in order to do this kind of operation. But another important problem related to the use of mathematical models is that even if you have data for your calibration, let's assume that we want to apply this model to a catchment like this that you can see in this slide. And in order to do the calibration exercise, you have to use the data that you have collected only at the catchment outlet, because in general, if you are lucky, you have data only on one point of the catchment, and in general, it is the measurement point is at the catchment outlet. So if you try to calibrate the model using the measurements at the catchment outlet, these measurements sometimes cannot be very, let's say, trustful, because if the catchment is large, what happens? It happens that the soil that is removed from the upper part of the catchment, which is in general the steeper part, depending on the catchment slope, most of this sediment is stored along the hydraulic path before arriving at the catchment outlet. So sometimes what you measure at the catchment outlet is not what it really happens within the catchments, because you can see sometimes a very small proportion of sediment that is detached and that arrives at the catchment outlet. And so for this reason, this calibration operation is very difficult if you don't have information on the relationship between the sediment yield at the catchment outlet and the sediment and the soil that was removed within the catchment. So in other words, you need information on the sediment delivery ratio, and this is very difficult to be obtained. So for this reason, even the application of the mathematical models, which is, now efficient. So you can see that there are 1,000 papers in the literatures that talk about application of the models, but most of them or let's say more than 95% of these papers are just simple and very, I would say, useless application exercise, because they don't use long-term measurement of soil loss in order to calibrate them, and this is wrong. Okay, so for this reason, because of the limitations of the mathematical models, some other scientists, including myself, try to use different approaches, and which is the third method that I want to mention here, and is the method which is based on the use of radio tracers. Okay, so in this slide, I just mentioned 4 radio tracers, more specifically cesium-137, excess lead-210, beryllium-7, and also plutonium-239 to 40. All of them are very effective, but they are different in terms of source. For example, cesium-137 and plutonium are artificial. That means that they come to the ground following rainfall, but it was, well, they are originated by nuclear activities, which is run by man. Okay. The other 2, lead-210 and beryllium-7, are instead natural. That means that they come to the ground by rainfall, but they are naturally produced in the atmosphere or in land. In my presentation today, I'm going to talk about cesium-137, okay, only one of them. And in order to have an idea of what cesium-137 is, well, it is originated, as I said before, by the nuclear tests that were carried out starting in 1954 to, let's say, the beginning of the 80s, even if there are some countries that still do some tests, like North Korea or other countries. But anyway, the greatest proportion of the activity stopped at the beginning of the 80s. So what about cesium-137, and what about the technique related to cesium-137? So cesium-137 is produced by these bombing tests. These tests release a certain amount of radionuclide of cesium-137, which goes to the atmosphere and is intercepted by rainfall. So rainfall comes to the ground, and so cesium-137. And once cesium-137 reaches the ground, let's see that cesium-137 is this little guy here. It is very strongly absorbed by the clay particles of soil. And so for this reason, it is a marker, okay? So it is very, very strongly fixed by soil particles. And then because of that, if we know a technique that can measure cesium-137, we can also try to monitor the movement of soil particles, because the soil particles removed by erosion, they take with them the cesium-137, which is linked to them, and then if we can monitor the movement of cesium-137, we can also monitor the movement of soil particles. That's why it is called the radio tracer, and that's why it is possible to use it for soil erosion study. One of the main important things related to cesium-137 is that when it reaches the ground, most of it will be adsorbed by the first layers, I mean the superficial layers of soil. So if we collect a soil sample here, what we have, okay, this is the soil depth from surface to 400 mass depth. And here there is a cesium concentration. You can see that this concentration is maximum at the surface, soil surface, and is decreasing with depth. So there will be a depth under which there will be no cesium detected, okay? And you can see this profile, you can see that we can use a mathematical model to interpret this profile, okay? And this is what we do in order to apply the technique. So how can we obtain a profile like this? We need to sample soils, okay? And in order to sample soils, we need a core like this. I don't know if the movie, can you see the movie?
Yes, we can.
Okay. Okay, so we can use this drill with this kind of tube core into which there is a plastic tube, plastic pipe. And then after that, we insert the core into the soil and we remove it. We can remove also the plastic pipe that contains the soils. And then we can use stuff like this in order to slice the soil. Can you see that?
Yes.
Okay, and then we can slice this soil little by little. Let's say each slice can be 1 or 2 centimeters, okay? And for each slice, okay, for each slice we can measure the cesium activity, okay? So at the end we have a profile like this, because the concentration is maximum at the soil surface, and then little by little it decreases, okay? So this is the sampling strategy that is used in order to reconstruct the profile, the cesium profile concentration into a soil. So how can we measure the content of cesium-137 for each slice of soil? We have to use the so-called detectors, gamma detectors in this case, okay? And you can see here a sketch of a detector. Usually the sample is put inside here, and on a special container that is called the Marinelli beaker. And this Marinelli beaker is placed over a germanium head of the detector, which is connected to a personal computer. And the personal computer with the special dedicated software can give you the peak of the spectrum of all the radionuclides in the soil sample. And you can see here a peak for cesium-137. The sample is put here, but it is protected by a lead shield in order to avoid that if you have, for example, radioactivity in the room, this radioactivity cannot contaminate the sample because of this lead shield, okay? And this is a sketch of detector. These are the detector in presence, actually, that I use in my office, in my laboratory at the University Mediterranean of Reggio Calabria, okay? Just to have an idea on how we measure these soil samples. Okay, so let's talk now about the first part of the presentation, which is the so-called traditional approach that makes use of cesium-137 to estimate soil erosion, okay? So the technique is based on a comparison. Okay, in this slide, you can have two soil profiles on the left and on the right. And the first one here is an undisturbed site. That means a place where during the last, let's say, 60 or 70 years, no erosion or deposition occurred. That means that you need to select in your area a flat area, or in top of a hill, for example, where you don't have soil erosion or soil movements, okay? So assuming that you are sure that all the cesium that came with the fallout, I mean, from the nuclear experiments, is there, okay? So this is called reference location, or undisturbed site, or reference site, okay? So a place where you can get the cesium reference value, okay? So how to get this? Okay, you have to collect the soil sample with the equipment that we saw before, the drill, and then you can reconstruct the profile. So in an undisturbed location, you can see that the cesium-137 is more or less represented by a yellow profile. So let's go now to an eroded site. I mean, one point where we want to know the amount of soil eroded. So in this place, clearly there was at the beginning the same amount of cesium-137 that came from fallout, okay? So at the beginning, you should have something like that. But because we got erosion in this site, that means that erosion removed the upper part of the soil. When we collect the sample, we have something like that. So if we compare these two profiles, we can see that there is a difference, and that difference will give us the amount of soil eroded, okay? And if we divide this amount of soil eroded times the years that passed since the beginning of fallout, which is 1954, to the date of sampling, okay, we have a value in tons per hectare per year, okay? So that's the main assumptions of the traditional approach. So this approach will give you the one value of soil loss, clearly once for each sampling point. If you have, for example, 10, 50, or 100 sampling points, you will have 10, 50 or 100 mean values of soil loss, okay? But, okay, so let's assume that, for example, we did a sampling today, okay, in 2022. So the traditional approach will give you the mean erosion rate for that time window, okay, from 1954 to 2022, okay? So that means that we don't know exactly what was the temporal fluctuation of soil erosion, okay, because we have just a mean erosion rate. But clearly with this approach, which is a traditional one, as I said, we have many advantages because, for example, if the technique works, we don't need traditional monitoring technique like plots, okay? Also, because we can collect many soil samples, many soil profiles, we can also study or have information about the spatial variability of soil loss, okay? For example, here you can see a catchment, okay? And the white circles here indicate the sampling sites. So if we have one value of soil loss for each sampling site, you can understand that by spatial interpolation, you can have information of spatial distribution of soil erosion. Okay, that means that we can have information on spatial variability. But also we can calibrate and validate soil erosion models, because as I said before, when we have to calibrate a model, we need data. And most of the time, these data are related to one point, like catchment outlet. But in this case, because we have an estimate of soil erosion for each sampling point, we can calibrate the soil erosion models using several sampling points, okay? And for this reason also, there is the possibility to construct a sediment budget for large catchments, for example, okay? But clearly we have some limitations. And the most important limitation is that we don't know what happened in the past. I mean, we know on average, okay, because CC137 explores that time window from 1954 to the date of sampling. But if there is a change in soil erosion during this period, CC137 cannot detect it, okay? At least the traditional approach. Also, okay, so let me try to explain better this concept, okay? Let's assume that we want to investigate soil erosion rates on a forest area, like that one that you can see here. And this forest area is there since let's say one or 200 years ago. Okay, so since then there was no change in land use. So assuming that, for example, we made a sampling in 2000, let's say 27, we have a mean erosion rate for all this period from 1954 to 2017. But if there was a change in land use, let's assume, for example, that this forest was interrupted in, let's say, in 1990, and the cultivation took place. If we do the sampling in 2017, we still have a mean soil erosion rate, which is related to the entire time window. But we don't know exactly how much it comes from the forest land use or from the cultivation, okay? Logically, soil erosion would be much higher for the cultivation, but cesium doesn't know that if it is applied using the traditional approach, because it gives you only one value. In order to have information on the difference in soil erosion rates related to the different land use, you needed to have samples in the past when the forest cover was interrupted, okay? Okay, so another problem related to the use of the traditional approach is that when you have to, let's say, calibrate or validate the approach, the CC137 technique, you also need experimental data, okay? Because sometimes, for example, I don't believe that CC137 is good. Just let's do this assumption, okay? And for this reason, I want to apply the technique and check if the technique is very well, let's say, suitable. And in order to do that, I need to compare the estimates of soil erosion with cesium with direct measurements of soil loss. Let's say soil loss that I have obtained from the plots. The problem is that when we have to compare the two estimates, we need to be careful, because the estimates provided by cesium-137 are related to a very long time window, okay, starting from 1954 to the date of sampling, in this case 2020. And in general, we don't have sites in the world with many years of measurements, direct observations of soil loss. So many people compare this estimate with this estimate for a shorter time period, because we don't have other, longer term estimates. So sometimes it's necessary to have longer term data sets of measurements, okay, in order to make this comparison possible. And so I will try to show you in these experiments how cesium-137 estimate improve if the number of years of measurements of soil loss from the plots are longer, are higher than the normal, okay? I don't know if I was clear, but anyway. There will, I think, Anatoly, can you confirm that maybe they can ask questions at the end? It's probably better that.
I think it's better. Yeah, we usually have like 30 minutes after the lecture
Okay,
to
perfect.
have questions
to discuss. Okay, perfect.
Mm-hmm.
Okay, so in order to see how the number of years of observations affect, the soil erosion estimates, it is necessary to use experimental data and to apply the technique based on cesium-137 using the traditional and also refined approach. I will talk later about the resampling approach, but now I can show you how, by increasing the number of years of measurements, the estimates improve. So to do that, I will go back to the plots, to my 5 experimental plots that were equipped in 2006, and for which we have 11 years of measurements available, okay? So the plots are located, as I said before, right here. This is Italy, this is Calabria region, this is my hometown, Reggio Calabria, and this is the study area, just about 30 kilometers north of my university, okay? These are the plots, okay? So these plots were established in 2006, and for each event, we have a value of soil loss. But here, I just want to talk about cesium-137. So with cesium-137, we undertook 2 main field campaigns. The first one in 2006 at the beginning of the experiment, and the second one in 2017, okay? So the first campaign in 2006 consisted of collecting 1 section core for each plot. You can see here, we selected only the point in the center of each plot in order to avoid major disturbance in the plots. And so for each of this core, we have a cesium profile. And these are the 5 profiles related to the 5 plots. Okay, so we have the total inventory of cesium-137 that was compared with the cesium reference inventory. So we selected another area, undisturbed, okay, where no erosion or deposition took place. And then we collected the soil core, and we established the reference value. You can see here the reference value that is higher than the inventory values of the 5 plots. That means that in these plots we have soil erosion, okay? And in order to convert the cesium loss into soil loss, it was necessary to apply, to use a so-called conversion model. I don't want to go into details about the conversion model, but this model is very simple. It's called the proportional model. And it accounts only for the bulk density of soil, the depth of plough or cultivation layer, the percentage reduction of cesium-137 with respect to the reference value, the time of sampling. Actually, it's the difference between the time of sampling minus the beginning of fallout, which is 1954, and then a particle size correction factor. Okay, so this model gives you the mean annual soil loss in tons per hectare per year. Okay, so these values are estimates of soil erosion using cesium, and we wanted to compare with the direct measurements of soil loss. Okay, and in order to do that, I'll show you how we collected the sediment samples in order to have the annual value of measure the soil loss. Okay, this is the tank. So for each tank receives the amount of runoff and sediment from each plot. And so when the event ends, we go to the field, we open the tank, we mix actually we dewater first the tank like this. Okay, and so the amount of turbidity and sediment in the bottom is very well mixed, and then some samples are collected from the top, okay, of each tank, and then these samples are transported to the lab, dried, and then the amount of soil loss is measured as a dry matter. Okay, so we made a first comparison between the cesium estimates, I mean soil erosion rate by cesium technique, traditional technique, with the measurements related to the first 4 years from 2006 to 2009. During this 4 years period, 15 events have been recorded, and you can see here that soil erosion ranged from 9.6 to 32.2 tons per hectare per year. Okay, so if we report in a graph like this, in a bar graph actually, we can see that this is the range of soil loss given by plots, and this is the estimate of cesium-137. What can we see from this figure here? That cesium estimate, soil erosion cesium estimate, is it is in the same range of plot measurements, but it is much smaller on average. You can see that it's shifted on the left side. That means that cesium-137 appears to underestimate soil loss if we assume that the plot measurements are correct. They are correct, but they are related only to 5 years that are recent years, from 2006 to 2009. But cesium-137 estimate is related to a very long time window, since 1954 to the date of sampling, which is 2006. Okay, so the two values are not really comparable, because cesium-137 is an average of a very long time window, and the plot measurements are related to a very short time window, only 4 years. Okay, so we cannot expect that the two values coincide. Okay, and why there was this underestimation? Because this underestimation, okay, these are the values, then about 11 tons per hectare per year given by cesium, and about 24 tons per hectare per year given by direct measurements from the plots. You can see that there are more than double, okay? But these results came up because during the last 2 or 3 decades, it was assumed that there was a climate change. That means that even soil erosion was higher. So what the plots say is that in that period soil erosion is higher than the average of a longer time window. Okay, and in fact, if we look at another parameter, which is the rainfall erosivity index, I don't know if you heard about Wisheneva-Smith USLE formula, in which there is the rainfall erosivity factor that depends only on rainfall. Okay, and because for this plot we had for other stations actually the values since 1954 to date of the rainfall erosivity index. Here you can see for 3 of these stations that there is an increasing trend of erosivity. That means that the soil erosion is increasing from 1954 to 2006. You can see here that there is a clear increasing trend. So that explains how cesium-137 underestimates soil erosion measured by the plots. So let's try now to see what happens if we extend the number of years of measurements from 4 years to 11 years by doing the second sampling campaign in 2017. You can see here the green circles are related to the second sampling campaign in 2017. And for each core, we have again a value of the cesium-137 inventory. Okay. And we did exactly the same. These are the related cesium profiles for each plot, you can see. And this is also the reference value measured in 2017 as well. It is very well close, very much close to the previous value that we had in 2006. And because the cesium-137 decays, okay, if we decay that value related to 2006 to the year of the second sampling campaign, 2017, from 5,000, it became 4,000, which is very close to this 4,000 directly measured in 2017. Okay, so we, in other words, applied the traditional model, the traditional approach twice. The first time in 2006, and we got an underestimation. And now the second time in 2017, in order to see how cesium-137 reacts. Clearly, in this case, we used much more data in terms of soil erosion direct measurements, because for 11 years, we have 131 events. Okay, so these are much more representative than the previous 4 years. Okay, And I would expect that cesium estimates will be closer than the first attempt. Okay, and in fact, if you can look at this comparison, which was the same that we did for the 2006 experiments, you can see that cesium-127, well, it falls again within this range of plot measurements, but it falls better than before. You can see here the previous one. Can you remember that? I think you can see the difference with the 11 years of measurements and 4 years of measurements. Okay, so this proves that if we increase the number of years of measurements, cesium-127 estimates are better than before. Okay, but clearly, even if in 2017 we got a 20.4 tons per hectare per year, this value is still lower than the mean value obtained for 11 years, which is around 29 tons per hectare per year. But it is explained again by the fact that we have this increasing trend for rainfall erosivity. So if we had the same amount of years of measurements, I mean, if my plots were established in 1954, and I had let's say 63 years of measurements, I would have expected that my measurements will be very close to the cesium estimates. But, you know, that will be impossible to prove because we don't have retrospective data. But cesium-127 is very useful to do that, okay? So from this point of view, we assume that if we increase the number of years of measurements, our estimates are going to be better and better. And you can make another attempt in order to verify this using a mathematical model. For example, using the Russell model. Russell model requires information on rainfall, soil, topography, and so on. And so because we have 11 years of measurements, we can calibrate the Russell model for these 11 years. And then we can extend the application from 11 years to the 63 years covered by cesium-127 estimates. And if we do that, and we did that, we got the Russell estimates in terms of soil erosion, which are, if you can see, very close to the plot measurements. Okay, that means that if we have more years of observation, our estimates will be much better. Okay, so this is the use of the traditional approach that is very useful if we have measured data to be compared with. Okay, but let's now go to the more, let's say, sophisticated approach, which is the resampling technique. What does it mean, resampling? Well, the meaning is included in the word. Resampling means that you have to sample the same site twice or more than twice. And we did that because in our experimental plots, we undertook the first campaign in 2006 and the second one 11 years later in 2017. So if summarize what we did in those plots with cesium-127, we can use this scheme here. And you can talk about this approach, which is a resampling approach, type 1, called the time-weighted difference method. What does it mean? Okay, so let's try to give you a simple explanation of that. We did the first sampling campaign in 2006. So in 2006, we had information on erosion rate for this period, 1954 to 2006, traditional cesium approach, okay? So we repeated the same investigation and same analysis 11 years later. So we had the erosion rate for the longer period, 54, 2017. Okay, I would remind you that cesium-127 traditional approach gives you the value of soil erosion in terms of tons per hectare per year. So if we integrate this information for all the time window, okay, for the first and the second time, what does it mean? If I multiply, for example, the value obtained in 2006, tons per hectare per year, times the number of years, I will get the total amount of soil eroded in those years, okay? And I can do the same here for a longer time window. Clearly here, I will have a much higher value, okay? So I integrated all the information of soil loss for a longer time window and for the shorter time window. So by making the difference between the longer and the shorter, I will get the amount of the soil loss in this time window, which is 11 years. If I divide this total soil loss times the number of years, 11, I will get a new value of erosion rate in tons per hectare per year, but related to that shorter time window, okay? That means that I use the cesium approach not as a traditional approach, but as a resampling approach, which gives us an estimate for a short time window. So if this assumption is correct, what I will get here should be coincident of my measurements coming from the plots, okay? But before showing the comparison, I wanted to show another, let's say, way to use the resampling approach. The first one was called, as I said, time-weighted difference method. The second one is a site-specific reference method. What does it mean? That in the first methods, we used twice the traditional approach, and each traditional approach needed a value of the reference, okay? With this approach, we use as reference inventory the values that we collected on the first sampling campaign. So the amount of cesium lost during this period can be converted into value of soil loss, okay? And this is another way to apply the resampling technique. Okay, so we directly convert the amount of cesium lost between the two sampling campaigns into a value of soil loss. And in this second graph, you can see the comparison between the plot measurements, the first method, resampling approach, and the second method, resampling approach. You can see that the values coincide, they overlap. That means that cesium-127 is very strong in calculating, in estimating soil loss. And this kind of experiment is very unique, because if you look in the literature, you cannot find anything like that. There is only one example in Canada that was made in 1987, if I remember well, using about, if I remember well, 10 or 13 years of measurements from plots. And so nobody did that because nobody tried to resample the same site for cesium measurements, and at the meantime they have direct measurements of soil loss. And you can see that this experiment demonstrates very well that cesium-137 can be used not just a traditional way, but also to obtain estimates of soil loss for shorter time windows. So to conclude my presentation, I think I'm in time. First of all, the overall results suggest that in our area, the recent period represents a time window during which the sediment response in the area, I mean the soil erosion rates, are increasing. Okay, and that was demonstrated by the application of cesium technique. And this is proved by the fact that the annual values of rainfall erosivity are also increasing. Also, the application of the resampling approach in both methods, I mean the time-weighted difference method and the site-specific reference methods, they were very, very useful, both because they match very well the measured data. But the first one was better than the second one. So in order to see if this technique is really strong, like I said, it would be necessary or suggested to extend this application for other places, and also to take account of the uncertainty analysis included in the study. And I think that's it. So if you have any questions, I just want to thank you for your attention. I cannot see your faces, but I assume that you are still there. I can say hello to Sergei Chalo. It is very nice to see you again, alive and kicking, I would say. And
hello, Paolo. Sorry for being late for your lecture.
Okay, so thank you very much for your attention. If you have questions, just let me know, and I will be happy to reply.
Dear Paolo, thank you very much. It was an amazing talk. I learned a lot during it. So, as usual, guys, if you have any questions, don't hesitate to ask them or write in chat.
Maybe I can start, Paolo.
Yeah.
Yeah. So again, sorry for not coming to the
No
beginning
problem.
of the lecture. Yes, it's very beautiful and inspiring talk. So beautiful presentation, inspiring talk. Yes. Paolo, can you just, maybe it's more like speculative subject, but it's quite interesting when we go listening for your presentation. What would you suggest, like scale in the approach? So I mean, cesium approach in terms of the possible spatial, let's say, extension in terms of the catchments. Can you, maybe you know from some experience that there is sort of large river catchments was covered on, or what size of the catchments was covered, but by the approach, what is in your experience the scale possibilities? So as far as there is in many, in some ideas, so we come to the interest if this can be applied to the certain size of the quite large territories. So
Yeah.
this is the question.
Okay. Clearly, I just needed to show this because it is very simple system, because it's a closed system, so everything is under control, I would say, because the plots are quite small, and then the scale effect is very, very limited. Okay, but as I said in one of my first assumptions at the beginning, when you extend, you know, the study, over larger catchments, for example, the uncertainty increases. Actually, we applied the resampling approach at catchment scales. But the problem is that these catchments are small, are around 1.5 hectares. But we have some deposition there. That means that, you know, we have on a smaller scale what happens on a larger scale. And then we saw that the results are still good if the uncertainties are taken into account. But in that case, clearly you need more measurements. You need also consider the spatial variability of each sampling point. And in order to do that, you have two options: or you have enough, let's say, detectors in order to analyze more and more samples, or to collect, as we did, for the same sampling points, 4 or 5 or 10 different samples, and then you can assemble then into only one sample in order to reduce the number of measurements, the number of, let's say, the time of lab analysis. But also there are so many other uncertainties related to technique, because I didn't talk, for example, about the accuracy of the conversion models. We still need to work on that, because in this case, I just used a very simple, the proportional model, because you know, there was no reason to use a more sophisticated one, because the plots were established in 2006. So even if the land was cultivated before, I think that using a more sophisticated model, like you know, the mass balance type 1 or 2, includes more uncertainty in the parameters, because it covers more, it requires more parameters, and you know, each parameter has its uncertainty. So we use a very simple model for this reason. But clearly, when you work at catchment scales, you need to account for many other things. But I think this is a starting point. So if you have the possibility, and you also have measurements, I don't know, in your case, if you have catchments monitored specifically for soil erosion or sediment tilt, and you have long-term data sets, that would be really nice in order to see if the technique works. Because I assume that you did in the past sampling for cesium analysis, right? So if you try to relocate the sampling points that you used in the past, and in the meantime your monitoring continues, that means that you still have data of measured soil erosion or sediment tilt, you can make this comparison. But I can tell you that it works even at catchment scale. Clearly, the uncertainty, as I said, is not like that in the plots, but it's a good way to use it and to start. I don't know if I answered to your question.
Yes, yes, Paolo. So it's
Yeah.
the direction that is right.
Mm.
Okay, thanks. So there is a Tole, would you continue? Or
Yes.
I can.
Yes,
Okay.
of course. So Paolo, can you see the question in
Okay, the
in the chat box? Yes.
Let me see. Let me see. Okay, thank you for your presentation. It was really nice. I would like to know if the short half-life is a problem for its use as a radio tracer. Well, I wouldn't say it's a problem because short half-life, which is 30 years, is not that short actually, because 30 years means that cesium-137 doesn't disappear after 30 years, but it is the content is half of the previous one. It means that in our case, for example, here in southern Italy, at least in those areas, because we also had a little Chernobyl contribution, around 20 or 30% actually, we still have cesium for at least 100 years, I think. So I think we can repeat this analysis in for other 3 or 4 times in order to see for different time windows how the technique works. So no, it's not a problem. Actually, yeah, it could be a problem where the cesium amount is very low, like in the southern hemisphere. But I don't know who is the person that Vanessa Garcia Gamero. Is that the name of the person?
Yes, it's the name of the person who.
It looks like from Spain, exactly. So I expect that you have more or less the same amount of cesium in Spain, depending on the area. Looking at the works that were done in Spain, also in the Pyrenees, for example, they have some Chernobyl contribution. So they have more or less what we have in Italy, in southern Italy, so around maybe 3,000 becquerel per square meter. That means that they can apply the technique at least for other 50 years as a minimum.
Oh,
Yeah.
and to this also the additional question: how, that's what you mentioned. What can be what is the increase of the cesium, which is estimated based on these global explosions in the 60s, so compared to the Chernobyl? So there is still also there's a research which is based on this time frame and comparative to the amount of the increase of the cesium. So I actually do not know the data.
Sorry, what was the question?
The question: how the, let's say, pollution by cesium is compared between the Chernobyl in this, I mean, in the European scale, and these global
right.
explosions.
Yeah, it wasn't made on this calculation, but it was a very recent contribution because I don't know if you saw my paper in hydrological processes, the special issue for deswalling. I don't know if you contributed. Maybe you contributed on that. Yes, there is a specific study on my catchments, actually on one catchment, in which we calculated the Chernobyl contribution based on national measurements of fallout, okay? Because we suspected several years ago that we got some contribution. So we tried to reconstruct the cesium fallout using national data, average national data. And we measured also on a reference area the total amount of cesium. That means that we selected an area that wasn't investigated in the past, a reference area. And we did a strategic analysis because we collected many samples and we got the profiles. So we assumed that that was the total amount. We reconstruct the cesium fallout using national data. And also we calculated using the IAEA software the amount of cesium fallout related only to bombing fallout. Okay, and then by difference we calculated the contribution of Chernobyl. And you can see that we have some variabilities in this area, not in this specific area actually, because that paper I'm talking about is related to another area in the Ionian Sea coast. And this one is in the Tyrrhenian Sea. But, you know, unfortunately, it was the only way to calculate the Chernobyl contribution, because in the past we selected another area where we could see the peak of Chernobyl contribution, but sometimes this peak is not very evident with respect to the rest of the values. Okay, but I'm going deeper in this problem because I'm starting now to find out if I can find some lakes, small lakes or reservoirs where I can get you know, the entire profiles to see if there is a peak somewhere else and to see if my calculations are correct. Okay,
Thank you very much. But before the question in the Zoom chat, we have a question from YouTube. Let me. I think you have already mentioned it, but anyways, from Alonso Zavala. Thanks so much for your presentation. I was thinking the same. What happened with the cesium in Peru? So
with this, what happened with the cesium
in Peru?
In
Peru.
Peru. Ah, okay. In terms of what? I mean, because yeah, I think it can be useful anyway, because I have no idea actually how much cesium they have. I know that it is still applied in Chile, in Argentina, and in other places of Latin America. I assume that they still have quite a good amount of cesium, considering that they have, I don't know which part of Peru it comes from, but I guess that in the mountain areas, they have quite a lot of cesium-137. And so, and also, I really don't know if the last accident in 2011 in Japan affected also Peru. I have no idea, because I know that it affected all the Pacific coast of North America. But I don't know if they have this additional contribution. So I assume that the amount is enough in order to apply this technique. I don't know if you, Sergey, have experience in those areas. Unfortunately, I don't know. I didn't see contributions in the literature about Peru, but I assume that I think the technique can be used.
Thank you. And I guess that it is we can now answer on the question from the chat about
Yeah.
other elements.
Okay,
so-
Artyom Katsura, is that correct? Thank you for your presentation. My question is, can we use other elements to calculate erosion? Of course. If for elements you mean other radio tracers, yes, we can. Because I mentioned in my presentation 4 of them. Cesium-137 was the one that I talked about, but also there is a lead-210, which is an alternative to cesium-137. As I said, cesium-137 is an artificial product of man, but the lead-210 is a natural product of Earth. And then it can be almost everywhere. And so it doesn't disappear because, I mean, even if it has a shorter half-life, only 22 years instead of 30, like cesium, its fallout is continuous. So its amount is in general higher, much higher than cesium. And so you can use that radio tracer, that element, to investigate soil erosion. But of course, you can use also the other radio trace like beryllium-7 that has a very small half-life, only 53 days. We did that in southern Italy, and it works very well, even in these plots that I talked about. And we made some analysis on beryllium-7 in the plots and in my catchments, and that was very useful. It is very useful, actually, to calculate soil erosion at shorter time scale, at the event scale. More recently, we started the investigation with plutonium-239-240, which is another artificial radio tracer, and it performed really well because actually we didn't publish a validation paper on that. It is still under scrutiny because it was submitted to a journal, and we are waiting for the approval. But we did that with the help of some colleagues in Switzerland at the University of Basel, and they provided the measurements of plutonium, and I provided the measurements of soil of sediment till. And so we are doing the same. We compare direct measurements with estimates, and at least in our knowledge and results, even plutonium-239-240 was pretty good for as a radio tracer. Clearly, you have many other methods. So, but I think that you meant elements as radio tracers. Is that right? Have I answered?
Well,
to you?
From my point of view, you have gave a perfect answer.
Okay.
And Artyom just proved it in the chat.
Katsura is from Japan, or?
No, it's from our university.
Okay. Katsura means seems to me like a more
right.
Japanese surname.
Okay, we can check it. Yeah.
Okay, very well.
So,
Can I ask some question?
Paolo,
One
thank you
more
very much. I guess. Are there some questions more?
If I can ask some little question about.
First, we're quite short in time, so Nikolai, please
Very
introduce
quickly.
yourself, and yeah, you're welcome.
Nikolai Sinsky, hydrologist. Can this initial profile of cesium be destroyed by a natural water moving or desorption in soil? So by the complex of processes that are not erosion, for example, can it be destroyed, and can it influence the classic method and your resampling method?
I really didn't understand actually What do you? So you want to know if
This profile can
the
be
profile can be disturbed?
can change. Yeah,
Can change.
can change, but not by erosion.
Not by erosion. Yes.
For example, but this
it is
option.
possible. It is possible that maybe you. When you resample, when you apply the resampling approach, in theory, you should recollect the soil in the same point where you collected during the first campaign. But this is not possible because that soil was disturbed by the first sampling. So you need to move a little bit, 1, 2, 3 meters from the original sampling point. Clearly, you need to consider that the profile can be disturbed. But the trick is that you don't have to consider only one point or only one profile. You need to account for this spatial variability. So you need to go there, relocate your previous sampling point, and try to collect not just one sample, but more than one in order to avoid the similar problems. Because, for example, if you have some animals that, let's say dug, the soils and then disturb the profile, clearly you have what you talk about. But in order to avoid this, you have to consider to collect more than one sample. And then you realize that, if there is some disturbance, maybe you can discard that profile and then you can use the other ones.
Yeah, thank you. I mean, to the desorption, for example, which is common for all.
Yeah, sure. Yeah, because it depends on the conversion model that you use. For example, in some profiles you have a peak, not on the surface, but just a little bit below. And this peak is assumed to go down little by little if you have migration of cesium-137. So if you use, if you realize that there is this migration downward, you have to consider that in your conversion model. If the question was that.
Yeah, okay, I see. Yeah.
So, Paolo, that's very big thanks for the lecture.
Okay, thanks to you for inviting me. It was nice to show my experiments and to see you all. And yeah, I hope that there will be another opportunity to very soon.
I also hope that it's quite important for the activities of our commission, as far as we agreed with the IACS that it's under this roof going on. Yeah, and if you, I don't know if Tol asked you, that's the recorded version of your lecture will be in YouTube channel. So if it's okay with you,
yeah,
then
no problem. Yeah, very well.
We'll keep it then here.
Okay, what about the meeting that the online meeting that we'll have on the 12th, December 12th? Are you will you be there?
Yeah, I'm planning to attend. Yes.
Okay.
Yes,
Yeah,
Tol can be also
nice.
as the young representative.
Very well. So try to be there because I think it's important. We need to talk about.
Is there, so it's not for all this Zoom discussion, but anyway, is there someone who is attending this February meeting, which was also from Professor Kudinek sent around from our commission? Did you also somehow manage it? Sorry, so again, there should be some meeting in, I guess, in Spain somewhere in.
Right. No, I don't think that I will be there. No.
Okay. Keep in touch on that.
Yeah. Unfortunately, I will be in Berlin for certain next year, but I will be in Poland at least for 1 month in Warsaw.
Yeah, talking about Berlin, maybe maybe we can just make a small announcement, just to notify everybody that there will be in 2023 the 28th IUGG conference, and our Commission on Continental Erosion will be there. And what is more important, that I just wanted to say that young scientists are eligible for applying or for a SISTA award. There's a deadline on 5th of January. This is a travel grant for young scientists. You need to meet all requirements, so you just need to be from a list of special countries. And you need to, I think, write a cover letter describing why are you planning to attend this conference. So we're waiting for your registrations and for looking forward to meet you there on our seminar and in our commission. Thank you.
Okay.
Yes, send the link, please, Tole, and
yes, it would be in chat.
Maybe we can also share the link on the website of the school.
Yes.
Okay. Okay. Bring my best regard to Valentin, because
we will just met 1 hour ago. Definitely, we will.
Okay. Is he okay anyway?
Yeah, all good.
Okay.
All
Perfect.
good. Thank you, Paolo, again, and it's very good to keep in touch.
See you soon.
Exciting lecture.
And keep
See
in
you.
touch.
See you.
Bye-bye.
See you. Bye.
Bye. Okay, and so with this we continue as far as we have quite a tough schedule somehow, and Tole, so we continue in this.
Yes,
in this
yes, we can.
Group, yes, and you will talk also in the same route. Okay, there will be the next point is the workshop done by Dr. Tsyplenkov. So I think Tole will announce himself actually the subject and the details of the talk. So how much you also will go in 1 hour, something like that?
Yeah, I think 1 hour, maybe 1 hour and 15 minutes.
Okay. Okay, then Tole, very welcome. The floor is yours.
Thank you very much.
Yeah, thanks.
So hello again. I think yeah, you have already heard about me. So my name is Anatoly Tsyplenkov. I'm from Lomonosov Moscow State University, and my research are mainly in sediment transport and soil erosion. And I'm really fascinated by our language, and therefore we decided that we can arrange this seminar, this workshop devoted to how one can estimate soil erosion in R. So during today's talk, I will give a small presentation to get you familiar with universal soil loss equation, and then there will be some initial modeling in R. You have all received links by mail today, where you can go to the R server we launched especially for this workshop. So I will go to it later. So let's begin. And first of all, I just wanted to talk about why should we care, and why should we why we decided to arrange this workshop. So our main aim of this next hour is to show how anybody using R can make a preliminary and reproducible assessment of soil erosion, almost for every point in every area on the Earth. So for these needs, we created a package. We call it a rustler. So it is just a wrapper around Saga.js commands and some other functions. It is mostly based on Terra package from RSpecial and RSaga CMD. I will show it a bit later. So, but the main aim of this package is to make it easier for you to run universal soil loss equation. So the question is, what is universal soil loss equation? So this is a really basic empirical model. You maybe heard of it a lot during the last few days, because it is like the basis of soil erosion modeling, and it's again general idea in multiplying all main soil erosion factors. So we have R for rainfall erosivity, K for soil erodibility, C for crop and cover management factor, so it's basically land use, land cover, P for conservation support practice factor, and LS, it's like a slope length and steepness factor, so topography factor. So as a disclaimer, unfortunately, I will not give a lot of attention to the P factor today, because it is a bit tricky question, and we just omit it. Unfortunately, this is some general practice in most of the soil erosion model studies which are done during last years. But anyways, it's life. So what are we going to talk today about? So Russell or Russell, so this model allows us to model only the detachment of soil particles. So this model doesn't account transport or deposition. So our results, we cannot treat our results as sediment yield or deposition. So it is like gross soil loss, so without any transport or deposition part. It was developed in the 50s by Wishmare and Smith, and it was based on a so-called standard usually plot with known length, steepness, and width, with a small sediment collector. And later on, these all erosion plots estimations were transferred to GIS, and where we can using different GIS techniques to calculate maps of different factors, and then in raster calculator just multiplying it, and voila, we're receiving a map of average soil loss in tons per hectare per year. So let's talk about factors and how can we calculate them. Initial equations are of rainfall erosivity, so the R factor. It was based on maximum 30-minute intensity of the storm, of the rainstorm. So, and of course, this data is something really rare nowadays. So you're really lucky if you can get this data on for your site, for your sorry. You're very lucky if you have this data for your area of interest, because usually all these calculations are later based on empirical equations which are using mean annual rainfall amount or some indexes like modified Fourier index or other stuff. But a really revolution, if I might say like that, in soil erosion modeling were in 2017 when a group of Panagas released a global rainfall erosivity database. It was a really great study. They created a 500 meters resolution map of annual average rainfall erosivity, and this is something which allows us to calculate, to make preliminary assessments of soil erosion for almost every part of the Earth. But you should be careful with the temporal resolution, because it is not presenting like contemporary periods, because for some countries, for example, for Portugal, you can see that it was based on data from 2000 to 2012. For example, for Russian Federation, it is based on the data from 60s and 70s. Therefore, there's a lot of questions about how, for what period can we apply these estimations. So the second factor we're going to talk is soil erodibility. So it is the factor K, which is describing how much soil is detached by one raindrop, and Wishmerer-Smith in their initial publication created a lot of nomograms which were describing main physical characteristics of soil. But later on, again, a lot of researchers created several empirical equations, mostly based on soil texture. So the percent of sand, clay, silt in the soil, and organic matter content. So for example, this equation from Williams et al. In 1983, it's one of the examples how one can calculate the soil erodibility based on soil texture and organic content. Again, there's some global data sets which allows us made some assumptions how high is soil erodibility in our place. It is a soil grids database. I hope you aware of it. So it is a really nice one, really high resolution. So this 250 meters global gridded soil data set. It contains a lot of information, not only about physical characteristics of soil, but other parameters as well. So, for example, for today's workshop, we'll use this soil grids dataset. So later, next one is land use and cover factor. It's also called a C factor. There's several ways how you can estimate the main aim of this factor is to qualitatively describe quantitative information. So how can we transform, go from land use, land cover classification to some real values or real coefficients? So some suggest to use some C factor equations, relationships with NDVI indexes, but honestly, they are really empirical and really regional, and most of the researchers nowadays are using table values. So some, for example, this research from Benavides et al. In 2018 in Hess suggested collected a really nice table describing how varying different land use types are in different countries and how different the C factor is. The next factor which is affecting the soil erosion, it is of course topography. Maybe it is like we should use like the third factor. Again, it is a qualitative way to describe the slope steepness and the length. Since it was produced for erosion plot with known steepness, it is and known length. So this factor is actually the way to transform our slopes on watershed to this standard erosion plots. And there are always some implications connected to this transformation, because it is not really straightforward how one can use these calculations. And I would say that the real boost for soil erosion modeling was done when I don't remember who exactly, but suggested to use flow accumulation threshold, so to limit maximal flow threshold modeled in GIS programs to several to 100 meters or 120 meters, and a second assumption were done by Simon Schmidt, so where they suggested to use various equations for slopes with different steepness, and this allows to scale LS factor for especially for mountain areas or for areas with a really diverse topography, if I might say like this. So this one was really helpful. And when we're talking about calculating of LS factor and soil erosion modeling at all, it's very important the input digital elevation model you are using to calculate this LS factor and to assess the topography, and because there are some studies showing that digital elevation models with big cell size cannot describe the real slopes. So they're describing them really roughly. So therefore, it affected the real soil erosion. So there, for example, in this graph, you can see that soil erosion tend to decrease with increasing of dam grid size. So the coarser the dam, the lower the modeled erosion is. Therefore, for today workshop, we're going to work with 1 meter digital elevation model to mitigate all these shortcomings, and we will see later on the results. Okay, I guess now we will switch to our studio. So in your in my last mail, I have sent you a link to our studio server. We run especially for this workshop. It is also there's also a link on our website. You can go to megapolis2022.ru, and you can find here's an R server link. So actually, your you will see such invite sign into RStudio. Your email is the username, and your and the password is the same for everybody. It is 2022. Okay. So I hope that you're aware of R a bit, but I think I will spend like 5 minutes describing the main features of R. So it is a programming language which was designed for statistical analysis, I think, in the beginning. But nowadays it is a really powerful language because it is a really community-driven language, and there's a lot of packages releasing, and you can do almost everything in R. For example, our website were done in R. Packages or libraries are attaching using the command library, but before this, the power of R is that you can run only one line of your code. For example, if you want to print hello world, you can write like this and then click run, and you will see an output hello world. And if there will be different lines of code, like hello and good bye, and the second line would not be run. So again, I'll just click run, and it was printed hello world, but it is not the goodbye line wasn't printed. So this is maybe obvious, but it's really essential for our workshop, because I will do everything in this window, and an output will be here. I'm sorry, there's some questions in. Okay.
Anatoly, excuse me, it seems that it works only in safe mode. You should push on safe mode.
Yes.
But I'm not sure.
Okay. Can you see the browser now?
Yes, we see.
Okay, perfect. Okay, so let me wrap up a bit. So the R is allowing us to run line by line your code, and this is sometimes really useful in your coding experience. So I will just repeat. You can press either run or use Control plus Enter snippet. So I will use it later. So if we will clear the output and print only the first line, you will see the output of the only first line, and our pointer is moved to the fourth line immediately, and now we can run the fourth line. Okay, so when we want to make some calculations, for example, we need to get the result of A plus B to make A equal to 2. We can use either it is common to use an arrow in R. It is like less and I am sorry, I don't know these terms, but this symbol is actually the way how you assign a value to your variable. So A is a variable, and this sign is a assigner. So this will make A equal to. So if we will print A, you will see the output is 2. And if you want to make calculations of A plus B, you will see that is equals to 5. So, and for other base stuff, so if you want to multiply, you use an asterisk. If you want to divide, you will use a slash and other stuff. So almost all functions in R are stored in packages or libraries, and when you want to use that package or library, you need to load it. For example, today we're going to use Terra package, and to load it, we need to write library Terra. So this is a package for geospatial analysis, and it using C++ in the backend. Therefore, it is really powerful and quick in calculations. It doesn't do any write on disk operations and store a lot of almost all your geospatial analysis results in memory. Therefore, it is really quick in comparison to other packages in R. So we will also use a package called library SF. It's a package for vector analysis mostly. And we will need also a package called MapView. So just a disclaimer, I'm using not the original MapView package, but it's forked by Joshua Eriksson because original MapView package doesn't support Terra package. So Joshua Eriksson wrote a MapView version which supports Terra, and yeah, this is big thanks to him for this. MapView package allow us to interactively plot interactively our results. You will see it later how it's helpful. So next we will use a library called R Saga CMD. This is a package which connect our Saga.js program with R. It is also using Terra package in the backend. So again, it is really robust and quick packages. So, and the last one, I guess, for it would be Rustler package, the one we developed especially for this workshop. So it's a collection of functions to calculate soil erosion. Okay, so we will deal today with small watershed in the Northern Caucasus. So first of all, we need to load some data. There is a digital elevation model which is stored in stored within the package Rustler. So we just need to write a path to it. So you will see that this digital elevation model is stored inside the Rustler package. So this is distributed with this package. So anyone can use it for your calculations. But this is only the path to the digital elevation model. To load it to R, we need to create a new object. We will call it dem Rust, and we will use the function from Terra package, Rust function, and it needs only the path to the file to be loaded, and that's it. Our digital elevation model is uploaded to R. You will see here that it has a class of special SPET raster. So it's a special class of rasters in Terra. There's some dimensions, the resolution. So it is 1 meter resolution. There is an extent of our digital elevation model. It's reference system. We're using UTM zone 38. And then some basic info about source and name. So, of course, we want to take a look on it, so we can plot it, and you will see. I'm sorry. So we can write a function plot with dem Rust, and you will see here that our digital elevation model is plotted. So what if we want to see where it is exactly? And for this purpose, MapView package is really useful. For example, we can use like MapView, then Rust, and there's some warning about really high resolution of our digital elevation model. Therefore, it is uploading really slow to the viewer. But in the end, we receive this beautiful interactive map built on leaflet. So you can like upscale, zoom in, zoom out, and see that okay, we are now in the middle of Caucasus, so near Bilim town. You also can switch to imagery here and see how the dam is lies on the satellite image. So very useful. Okay. Also, we need watershed border or catchment border. Again, there's a shape file stored distributed within the package, so you can write it like here. It is watershed.shp package Rustler. Okay, so we can upload it as using vect function from Terra. It is again really simple. We just need to write path to our shapefile, and our shapefile is uploaded. We can plot it now, again with plot function. We also can plot it with map view. Okay. We also can plot together digital elevation model and the watershed by adding a plus sign between different map view calls. Again, I'm sorry, I forgot about the high resolution of our digital elevation model. But anyways, we will see the results pretty soon. And if you want to know the size of your watershed, there's also a function in Terra package expands function that allows us to calculate the size of our vector in meters. Yeah, so if we want to know the size in square kilometers, we just need to divide it by 10 by 1 billion. So our watershed is 1.88 square kilometers, I guess. And by the way, our watershed and digital elevation model uploaded to the viewer, and you can see that they're lying almost perfectly, and that our digital elevation model is a bit bigger than the original than the initial watershed. So this is something we need to deal with, and I will now show how. So, okay, first of all, let's start with LS factor. Since this is a co-causes, we will use LS alpine function. There's a we'll create a new variable ls rust, and using ls alpine function from Rustler package, we will now calculate the ls function ls raster. So this function need you to write the link to digital elevation model, then the threshold of flow accumulation, the one I told in slides, and also it is very important, we need to write here the path to the Saga object. So we need to link our packages with Saga JS, which is also installed on this server. So therefore, we need to write this function. So we need to create one more variable. We call it Saga, and we will use a function from rsaga kmd. It's a Saga JS function, which search our machine, our computer, for installed Saga JS, and upload it, connects it with our R session. But it's very important to write here the raster backend variable, because we want to use Terra, and this is an important step, because if you make a mistake here, nothing will work today. So we will just wait a bit while it is searching for the whole server. While it's uploading, we can write an ls alpine function. So our digital elevation model will be digital elevation model rust. Threshold, we will use 100, the one which is recommended by authors, and we need to also specify the Saga object. So Saga object is equal to Saga variable we just created, this one. So if you I will run it, you will see that this is just a description of all Saga variables. So please, there's a lot of functions in Saga, so just don't run like I did, because yeah, it's almost endless. Okay, so now we'll need to calculate the ls alpine variable. So we will run this line, and it takes some time, because what is going on inside this inside this function? It creates a flow accumulation, then it calculates also slope of our digital elevation model, then creates a threshold variable, reclassifying the flow accumulation variables, and then applying all equations to calculate slope steepness factor and slope length factor, and then returning us an spat rust object. So here you can see that ls rust is a spat rust object. We can also plot it, and you see here that yeah, we can see that almost all our territory is covered by ls varying from 0 to 50, with some outliers in somewhere in the center. You can see this really green pixels. Again, we can explore in depth what we modeled just now using mapview function from mapview package. Just to speed up the rendering of our rasters, I will use an aggregate function. So we will like upscale our raster 5 times, so it would be much more quicker to render. Okay, yeah, we can see that somewhere here is just a really high, really steep slope, and it seems to be really short, and therefore this is the highest places where with the highest ls values. Yeah, and yeah, just I wanted to mention that we have a lake here in the downstream part of our watershed. There's a lake, and it is equal to 0 here, our ls factor and ls variable, because it was already filled digital elevation model as an input for ls factor calculations. So okay, what we need to do now is to crop our raster to the boundary of our watershed, because if you remember, our watershed is a bit bigger than our raster. Our digital, oh no, everything is mixed up. Our watershed is smaller than the raster, so we need to crop this part, and this can be done by using a function crop from Terra. So we will create a new variable ls resampled, and we will crop ls rust, and just sure that you specify the first one, it is raster we're going to crop. The second variable is the object we're going to crop with. It is ws, and we need to use a parameter mask equals true, to be sure that we crop everything outside the watershed. Okay, so it is calculated already, and we can now plot it and see what happened. Okay. Oh, I made a mistake, and also so just need to wait a bit. So while it is loading to our viewer, we can discuss a bit next steps. So we will now discuss about soil, talk about soil erodibility or K factor. For this needs, there is special functions here. So we can see now that our raster is cropped to the boundaries of watershed, and so everything is fine and we can use it. Now, okay, so we'll not need this anymore. So K factor. There are several functions in Rustler package we need to know to use to create a map of soil erodibility. First of all, we will use we need to download soil grids dataset, and for this purpose there's a function get soil grids. You can see a description here. So it has only 3 parameters. First of all, it is our area of interest. Second, it is like a layer we are interested in. It's not possible to download all soil grids, unfortunately. We're now limited only to sand, silt, clay, organic carbon parameters, soil pH. It is about density of the soil, and also the amount of coarse fragments in the soils. But now we will need only sand and silt, clay, and SOC parameters for soil erodibility calculation. And for this purpose, we need to specify an area of interest, and I will now show you why this is important. For example, we need to download sand. We'll create a sand test variable. We'll use get soil grids. Area of interest equal to our watershed border. WS layer is would be sand, and prediction quantile we'll use by default mean, so it is not necessary to write it. Okay, so now it is going to the internet, downloading soil grids dataset, cropping to the borders of our watershed, and transforming it to Terra object. So now we get SPET raster with 3 different variables. So if we will plot sand test, you will see that there's actually 3 rasters because there are soil grids allows us to get physical parameters of the soils for different layers in the soil profile, for 0.5 centimeters, from 5 to 15 centimeters, and from 15 to 30 centimeters. So now we need to aggregate them and to create like a mean assessment of mean amount of sand in the first 30 centimeters in the topsoil properties of our profile. But before this, we need to get sure that our watershed is covered completely by this variable, and we can do it by map view again. Okay, and you can see now that unfortunately not all watershed is covered by our soil grids raster, and this is because of the cell size of the soil grid. It is 250 meters, and therefore that that part of the watershed, that cells that are not completely covered by a watershed are omitted. So this is a small disadvantage of Rassler package, and this is something needed to be edited later. So for these purposes, we need to create a new variable. So we will create a buffer area around our watershed. So to be sure that we will download soil grids for the bigger area, and then we will crop our soil grids raster to the borders of watershed. So for this purpose, we'll create an area of interest object, let's say called vect, and we will use function buffer from Terra package. We just need to specify which area we want to buffer. It will be WS object, and the distance of the buffer, it would be, let's say, I don't know, 500 meters. Okay, and now we received a buffer around our watershed, and now we will okay. Now we will use this variable as an input to get soil grids per function. So we'll create now send variable get soil grids. Our AOI will equal to AOI vect parameter. Layer would be send. Okay, so we need to make the same thing for silt. For the clay. And also for the organic content. While they're downloading, let's talk about their dimensions. So if you see here that our send has vary from 2095 to 295 to 310. That's why, because it is stored in I don't remember, but I guess this is a thousands of percent, and we need actually percentage of sand in the soil profile. Therefore, we need to divide it, or we can use a function aggregate soil grids, again from Rassler package, which allows us to aggregate like every layer and get like mean value for the whole topsoil property. So and it also scale to conventional units, not scale, converting to conventional units according to soil grids website. So we will use sand Rust object, and we will use aggregate soil grids with send parameter. And it returned us a spread rest object with mean sand content for the whole topsoil layer. So this should be repeated for every of the variables. So we need to do the same for the clay, for the silt, and for the soil organic content. So it should be clay, silt, and soil organic content. Okay, so this should be run, and now we have mean amount of clay, sand, silt, and organic content in the topsoil in every cell of our raster. Now we need to calculate, based on these physical properties of the soil, the soil erodibility, and this should be done with k-factor function. So there are several parameters here. First of all, this is all rasters we just created, and the method we wish to use in calculation. We will use the default Williams 1983, the one I just showed in the presentation. So we'll create a new variable k-rust and use function k-factor. We'll just like wrote here, send rust object, silt, rust, clay, rust, and sock. Okay, so it applies this equation from Williams et al. And returns us our initial return us the desired soil erodibility map. So if we will plot it right now, you will see that we have a raster of soil erodibility for our area of interest. It is bigger than our watershed, so we need to crop it. But we need not only to crop it, we need to resample it to the resolution of our digital elevation model, because in the end we will multiplying all our factors together, and this is essential because we need to be sure that their extent and cell resolution is the same. So otherwise it would not be possible to run this multiplication. For example, if I will just right now k-rust, the one we just created, multiply by ls resampled object, we will get an error because extents doesn't match. Don't match, because first of all we didn't crop it and we didn't resample it, so we need to create a new object, k resample. Oh, I'm sorry. We first of all we need to crop. Okay, we'll k crop. It would be crop k. No, it should be first resampled and then cropped. So k resampled. Resample function from Terra. We will use I think ls resampled object. Oh yes, I'm sorry. K rust and ls resampled. Okay, so now our k factor raster has a resolution of 1 meter. And now we need to crop our resampled K factor to the border of watershed. So we'll create a K crop variable and use a crop function K resampled and watershed variable, and just write mask equal true. Okay. Now we have our watershed K factor raster cropped to the border of the watershed and resampled to the same resolution as we have with digital elevation model. So if we will plot K crop right now, you will see how smooth it is. Yep. Okay, perfect. Now it would be possible to us to multiply LS with K factor. Okay, yeah. So this is unnecessary because this is meaningless, but we just make this to be sure that everything is worked. Okay, so K factor is ready. Next step would be rainfall erosivity. Again, for this one, we have a function getGloret. It is really simple function. This is the one which allows us to download the Gloret dataset from Panas Panegas et al. To our area of interest, and yeah, it's the only purpose of this function. So we just uploaded this Gloret raster to the cloud. Made it. We made it cloud optimized GeoTIFF, so it is now easily wrapped by GDAL functions. So to get R factor, we will need getGloret for our AOI variable, and that's all. We just need to wait a bit, and voila, our R factor is downloaded. So we can also plot it, and you see that it is really coarse. Of course, it is rough because it has 500 meters resolution. So again, as with solid grids, we need to crop it and to resample it to the border, crop it to the border of watershed and resample to the resolution of digital elevation model. This, I will just repeat the same we just made with K. So we'll create a R resampled object. We'll use R factor, and R crop would be R resampled cropped by watershed. So now we will see that the resolution is 1 meter. It should be a really smooth one. Okay, yeah. Now it's perfect. So we get ready with our rainfall erosivity. So now we need to use the last factor. It is cover management factor. Unfortunately, for this one, there's no special functions in Rustler package, because it is always really tricky to get. It's always very tricky to get the right land use map from global datasets. So this is something you need to acquire by your own. For these purposes, I have uploaded our manually digitized land use land cover map, and so this stored in system files, data course, and I think it's LULC shape file from package Rustler Okay, yeah. So this is a vector, so we need to load it as a vector. We previously used vect function from Terra file, from Terra package, but this time I want to use SF package because it is much more easier to do some operations with the tables in shape files using the SF package. So we will create a new variable LULC-SF using stRead. We'll create our variable. So we can now take a look on it. You will see that there's a simple feature collection with 74 features and 2 fields. Okay, so the field we are interested in is LULC, so land use, land cover. We can also plot it with using map view. Oops, map view. LULC SF. There's a usable parameter in this function, that call, which allows us to specify which column of the variable we should use for symbology. So this would be LULC column, and you can see now that here we have this package, or sorry, this map of land use. So, but we need to create a C-factor raster to use it in our calculations, and therefore we need to reclassify this shapefile and then rasterize it. So for these purposes, we will use deploy R package. Okay, because we'll create new variable reclass, and we'll use mutate function from deployer, which allows us to mutate the table of the LULC-SF shapefile. We will create a new column. We will call it like C value. Okay, and we will write a complex if-else statement using the function case when. So we need to specify that if our shapefile equals, if land use and cover class equals to sharp. Yep. So in this case, we will say that C factor will equal to 0.005. If LULC equals to forest, our C factor would be 0.001, and if LLUC equals to pasture, it equals to 0.01, and if water, then it equals to the 0. So you might ask me where I just get these variables. So again, as I described in the beginning, so this is a table variables from previous research. I just used min parameters. For now, I will describe this part a bit later, but just keep in mind that these values were taken from tables, so it's not from my head. Okay, so we can run it and check if everything goes right. Okay, so we can see now that there's a new column created, C value. Perfect. So next step would be to rasterize our reclassified shapefile. For this purpose, we'll create a new object LLUC vect. So this will just transform from SF package to Terra package. Our shapefile LLC reclass. So now it is SPET vector variable. Next, we need to create raster object. We'll call it like this. So this is empty raster, which uses the extent of our land use land cover vector. But we need to specify that there will be amount of columns the same as in our ls resampled object, and amount of rows the same as in ls resampled object. Okay, so it would be 222.44 rows and 1373 columns. Okay, so we just created this dummy raster object. So as you can see, it is empty. If we will plot it, there will be nothing. Okay, because path raster has no cell values. So now we need to write there our C factor values, and this is where we're creating the C factor raster. So we'll use rasterize function. We'll use LULC vect variable. Then we need to specify raster where we will rasterizing our variables. Okay, and afterwards the parameter in vector file where is the C values are stored. So, and this is parameter has C value name. Okay, so in the end we receive a C factor Rust object with the same resolution as in ls, with the same reference, and yeah, I think that's all. So now we can check it and plot. Okay, perfect. Now we can see that we have our C factor raster. So that's almost it, because next step it would be just multiply all our resampled variables together to create a Russell object. So for this purpose, we're using C factor Rust multiplied by let's see, R crop multiplied by our K crop object, and with our ls resampled. Voila, no errors. That means that our Russell calculations is finished. So let's explore it. What have we have here? So this is a class of SPET raster with the same dimensions as our digital elevation model, as our ls resampled, the same coordinate reference. It is in memory. It has wrong name because it takes the name of the first variable we used in multiplication in equation. And here are some min and max values. So what can we do now? First of all, I prefer to change the name of our raster, and this can be done with base function names, Russell, and we call it Russell. Okay, so now we have our name is equal to Russell. Perfect. Next step, I think we're most interested in mean soil loss variables. So this can be quickly assessed with summary function. Summary Russell, and you see that our mean soil loss is 16.33 ton per hectare per year. So yeah, just to do not forget, our results are in ton per hectare per year. But there's a warning that the summary used a sample, and this is not really critical now because we have a really small watershed, but this is a really important in a bigger part. So to get a more precise assessment of mean variable, we should use global function. So it's just called global. I'm sorry, global. We write here Russell. Then we need to write function we need to get. So we're interested in mean, and a special parameter that we are not interested in empty cells. So we need to omit them. So we just need to write na.rm equal true. Okay, so we see here that actual mean value is 16.37, not 16.33. The difference is not that big, but just keep in mind it. Okay, we're also interested in total soil loss. And for this one, we can use again global parameter, global function, but instead of mean, we can write here sum function, and we will receive total soil loss in ton per hectare. But our digital elevation model is in meters, and so we need to convert from hectares to meters. And if you are familiar with this units, 1 hectare is equal to 10,000 square meters. Yes, so to get results in tons, we need to divide our summary soil loss by 10,000. Yeah, okay. So that's it. That is the final result. It is total soil loss of our area is 372. Okay, perfect. But it was a really long introduction with almost 200, not introduction, long presentation with almost 200 lines. And maybe you're still wondering why this is important for our modeling. And I would want to say that you remember how I just name that, and I just took C factor values from the table, and this is the most critical point of every soil loss equation calculations, that actually we are not really know for sure what is the C factor value for every land use land cover class. Therefore, Batista et al. Suggested a really nice approach, which I really suggest you to read and to explore. It is a way how one can using Monte Carlo simulations to test different C factor values and different R factor values, K factor values, knowing the parameters of the distribution of these factors. So what they have used, so they created almost 100 alternative rasters of C factor, K factor, R factor, LS factor, and so in the end they received almost 1,000 of alternative values of erosion rates. And this is a way of how can we assess the uncertainty in soil loss estimation, and that's why it is necessary to run soil loss equations in R, because in GIS programs it would not be almost impossible to you to run 100 simulations, while in R it would be really easy to write a for loop and simulate almost 1 million of alternative values for your soil erosion calculations. So I just want to finish my talk with by citing Twin Peaks that we almost never know the results of their soil loss equations models. Are they real or not? And therefore we need to run as much as possible alternative runs, and only combination of different parameter sets can give us meaningful results. So that's it. I'm ready to answer any questions, and I'm encourage you to write me if you have any questions about Russell modeling, about what MCDM, and if you want to take part in developing this package, so you are free to join and to contribute on GitHub. So thank you very much.
Thank you, Toля. And so I think also it's quite clarification for the participants, and also especially for international participants, that's the contacts of Anatoly and are available, and after introduction to this very detailed approach, you can follow Anatoly as well directly, and this is quite also nice for continue this workshop. Anyway, there are a few questions in the chat as I see. I can read, or what's how you prefer?
Okay, I can see them. I think I can just read them out loud. So no, unfortunately, Rustler is not on CRAN yet, because it is just now under development. I'm not yet finished it, so it has some problems with documentation and with some dependencies. Okay, the second question: can the model take into account the features of the permafrost zone, for example, the iciness of soils? Well, honestly, I'm not the one who should answer this question. I think it would be better to ask Mikkel Marker or Paolo Porto. But I would say that from my point of view, it is possible to use some icing information in soil profile to calculate soil erodibility. You just need to be clear about what equation you're using for soil erodibility assessment, because as I said, there's a bunch of different empirical equations and you need to be really accurate in selecting the perfect one.
I can briefly also add there are a few plots which were specifically developed in the permafrost zone, and these flumes experiments were related to parameterization of the factors. Firstly, soil factor in terms of the impacts of the iceness and other possible permafrost-related effects in the erosion process. But this is like a very specific and very, in some way, very poor developed story in all the soil erosion modeling, as far as most of the, as well as Anatoly and Mikhail Merker 2 days ago mentioned that mostly this approach is based on the experiments in the agricultural areas, which are not related to permafrost zone. Yes, so thanks, Anatoly. And there's more questions in the chat.
Yeah, so I will upload the today's code to the website of the conference, and there's also would be an update of the package with vignettes, so you will see how can you use not only universal soil loss equation, but also how can you use what MCDM model with this package. So just keep updated.
Okay. Anatoly, and can be interesting also to mention for the wider and not very deep in this topic participants related to your comments that all this approach is not very precise in terms of the results, and no one knows the accuracy of the calculations, and that their alternatives are requested, possible. Can you comment on that? Which alternatives would you recommend, and what is your vision on the topic more specifically?
Well, I think all other models that were mentioned by Paolo Porto or Mikhail Merker should be, or also by Andrei Zhitkin, should be taken into account, because universal loss equation is like the basic one. It is really simple, and more complex models can give us more precise results, of course. But I think, from my point of view, the power of universal soil loss equation is in its simplicity. So this allows us to run as much possible variations of different factors as we want, and so we can create an ensemble of Russell models. Therefore, maybe somewhere in this ensemble of results, the true value of soil erosion would be. Okay. So I think there are some connection problems with Sergey Chalov. Okay. Yes, Artyom, I would share reference and other links. So I think I will just upload my presentation as well as a code to the conference website. We will notify you about this upload by email. So actually, we will upload all lectures of all lecturers as a PDF files on the website. We will notify you by email about this. Okay. Okay, so I guess if there are no questions more, okay, Sergey is back. So if there are no more questions, I guess that it is my pleasure to finish today's seminar. I would say that the RStudio server I was referring to you in this workshop would be on for I think next 2 or 3 days. So you're free to you are free to test your own results there. So thank you very much for attending this, and we're looking for you on tomorrow lecture by Professor Sadeghi from Iran. He will give a very interesting talk about I'm sorry about watershed health assessment in hydrology. It's a really interesting topic.
And tomorrow we will also send around the questionnaire for the participants, and we will carefully be happy to get the replies as well.
Yes.
Yes.
So thank you very much,
Anatoly. Yes, and thank you all participants.
Yeah. So ciao.
Ciao.